Okay.
Hello, everyone, and welcome to our latest DZone webinar. My name is Jason Cockerham. I am the Community Engagement Manager here at DZone, and we're glad you're here today. We've got a really exciting topic, and so we're happy that you've joined us. If you're new to DZone, we are one of the world's largest online communities of software developers and experts. We publish all sorts of knowledge resources for developers and really anyone passionate about software development. We've got all kinds of things like ref cards and trend reports and thousands of articles written and published by our community and a bunch of great events just like this one. And all this kind of stuff makes us the go-to knowledge hub for software developers all over the world. If you want to see more of some of the events that we like the one we have today, you can check out our website at dzone.com/events. There we've got all of their past events, upcoming events, and everything there that you can check out. Today, we have joining us Eric Hansen, Siddharth Gupta, and Matt Brown from SingleStore. Eric Hansen is the Director of Product Management at SingleStore DB, and he's got extensive experience in data management, warehousing, analytics, big data, and streaming, and all kinds of stuff. He's an expert in in-memory column store and vectorized query execution technology. And he also has a deep knowledge of data warehousing, customer use cases, scenarios, challenges, best practices, pretty much anything you can need to know about it. Siddharth is an enterprise solutions engineer with SingleStore with nearly 10 years of experience in big data technology platforms. He has an in-depth knowledge of master data management, data visualization, big data analytics, and service-oriented architecture, and he's well-versed with big data technologies on AWS and GCP. And then finally, Matt is the head of commercial marketing at SingleStore. He organizes their cloud dev days, technical workshops, and speaker events. You can find him on LinkedIn, and there you can receive all kinds of upcoming product release news, code tutorials, and all sorts of other really useful developer content. Matt is going to jump in towards the end and facilitate our Q&A with the last few minutes we have left. So be sure to get your questions in as they come up throughout the presentation. But first, Eric and Siddharth are going to walk us through the process of using SQL to drive facial recognition and image matching capabilities. Fascinating. They're going to show us how to use the dot product function to achieve facial image matching from 16 million records in just 5 milliseconds. I'm sure we can all appreciate just how much more data we can process with that kind of performance. Lastly, DZone is all about community. So we encourage you to get involved and get engaged in the conversation today. As I mentioned, we're going to have a Q&A towards the end. So as questions come up and as you think about things, there's something that you see on the screen you just want some more clarification on, be sure to type your question into the box on the right-hand side of your screen, and we'll be able to answer those at the end. So at this point, I'm going to stop talking and hand it over to Eric, and he's going to walk us through what they have for us today. Eric, take it away.
Hey, thank you, Jason. So, it's my pleasure to talk to you today about how you can do facial recognition and other kinds of image recognition through SQL with SingleStore DB. So first, a little quiz. So yes, you can do face matching with SQL and SingleStore, but to give you a little flavor of the kind of things that we can do with our face matching capabilities. First, is this the same person? That's question number one. You can think about, is that the same person or are those two different people? And do you know who it is or who are they if they're different people? Okay, I'm not going to answer right now. We'll get to the answer later. And then the question is, can SingleStore tell if these are the same people or not? So we'll find out. So just remember this and we'll come back to this. So I know a lot of you are new to SingleStore. So first, you might ask, what is SingleStore DB? So SingleStore DB is a distributed SQL database management system. It runs in the cloud and a platform as a service called SingleStore DB Cloud. And you can also run the SingleStore DB software on premises, or you can self-host it, wherever you want on your own systems. And it supports both transactional and analytical workloads on the same system. It's really, really fast. It uses scale out. It compiles queries to machine code. We got a plan cache, so when you run a query one time, it's parameterized, and then if you run the same query again with different parameters, we can look up the query plan that we already compiled and run it again with those different parameters. We also support what's known as vectorization or vectorized query execution in our column store, where we essentially process batches of rows at a time and process a bunch of rows worth of data in a very tight loop in arrays to allow you to do phenomenal performance improvements for analytical queries. And we also use single instruction multiple data, or SIMD instructions. We use the Intel AVX2 instruction set to do that. And of course, that's available on all the modern Intel chips built in the last 6 or 7 years. It's also available on some competing chips as well that are compatible with Intel. So on the right is a picture of a what's known as a SingleStore cluster. Client applications can connect to an aggregator node. They submit their SQL statements. They get compiled there if necessary. And then your data is horizontally partitioned across a set of leaf nodes. It's also known as sharding. You can also say that it's sharded across the leaf nodes. And so aggregators know either if they know what data, what leaf node contains the data relevant to a query immediately, they can just send the query directly to that leaf node. Otherwise, they can broadcast portions of the query to every leaf node to run the queries in parallel. So our customers are running on anything from a single core all the way up to a couple thousand cores on a large cluster. So you can use this for all different scales of applications. And SingleStore is also multi-model. That means we support multiple different sort of data models within a single database. So we obviously support relational database access through the SQL language. We support unstructured data access via a full text search feature that, again, you can access it from SQL. We support geospatial data types and operations, time series operations, key value lookups at very high rates, and we support semi-structured data through a JSON data type. All of this is accessible through SQL. And several of our customers have gotten tremendous benefits from our multi-model capability. For example, Uber is using geospatial and time series. Armis got tremendous speed ups using SingleStore. Under Elasticsearch, they didn't get the performance they wanted. Queries that were timing out with Elasticsearch now process in less than 10 seconds with SingleStore. IEX Cloud consolidated 3 different data engines, MySQL, Redis, and ClickHouse, just into one system, SingleStore DB. And Fathom also is benefiting from consolidation by allowing them consolidation of an application which used to need Redis, DynamoDB, and MySQL now just into SingleStore. So this multi-model capability is really powerful and allows you to simplify your application environment. And we also support vector similarity matching. So that you could think of that as yet another pillar of our multi-model capabilities, and I'll tell you a lot more about that. Our product strategy is a cloud-native approach. We're building technology for the cloud and distributed environments where you can do real-time analytics. So what real-time analytics is if you're doing analytical queries like group by aggregates and star joins with aggregation, window functions, et cetera, on rapidly changing data as soon as the data is born, that's real-time analytics. SingleStore is amazing at real-time analytics. Most of our customers start with SingleStore for a real-time analytics use case, and then they often broaden to more pure analytics like data warehouse type operations, as well as transactional operations. We're capable of all those things, and we really shine at real-time analytics. And then distributed SQL is a term that reflects the ability to do transactional style applications in a distributed SQL database. We support transactions, high availability, disaster recovery, extremely fast single row lookups and updates and upserts, all on a SQL platform that's distributed. And we are continually striving to improve our developer experience, allowing you to do things like built-in functions, user-defined functions, stored procedures, our JSON data type, a rich set of built-in functions for operating on JSON, a rich SQL dialect, and more. And finally, we integrate with a partner ecosystem with, hundreds of different partners. Technologies can work on top of SingleStore. We're highly compatible with MySQL, so many top products that work with MySQL will just work directly with SingleStore because we are compatible with the MySQL SQL dialect. So before I get to the details of face matching, I just wanted to, and I'm going to, as you heard at the beginning, we can do face matching incredibly fast through SQL. First, let's take a little trip through what makes SingleStore fast in general. So it's a shared nothing scale out architecture, as I showed the picture of earlier. We have an in-memory row store. It's based on an in-memory skip list. A row is essentially a C struct, and queries are compiled to machine code using the LLVM compiler generator. We generate Intel x64 instructions. The result of this is that we can process 10 to 20 million rows per second per core on in-memory row store data, compared to about 2 million rows per core for legacy B-tree-based database systems, like Postgres, MySQL, SQL Server, Oracle, et cetera. They're more like 1 or 2 million rows per second per core. With our in-memory row store, we can do equivalent operations at about 10 or 20 million rows per second per core, do the in-memory and compilation. And we can do row lookups and updates in sub-millisecond time. So this is available on SingleStore. We also have a column store. Our default table type is a column store. It is disk-based, so you can store as much data as you want. The data can be much bigger than will fit in available RAM. On column store, we use vectorized query execution, where we process data in batches of about 4,000 rows at a time, and we can process each column within that batch in a really tight loop. So we can do just phenomenal levels of performance. We can get greater than 100 million rows per second per core for typical, scan and filter and group by type operations. And for some operations that are really in our sweet spot, where we use operations on encoded data, that means we operate directly on compressed data. We don't even have to decompress the data before we apply a filter or do a join or a group by, for example. And we use the Intel single instruction multiple data, or SIMD instruction set, to do this faster. So for certain operations, we're able to process more than 1 billion rows per second per core, when we are able to do the operations on encoded data. And there's a really cool YouTube video. It stood the test of time. It's a few years old, but we process in the demo in the video, we can process 1 trillion rows per second on a single cluster. And we've evolved this column store technology into what we call universal storage, where we added indexing and seeking capability, so you can do transactional applications on top of our column store. And as I said, it's a default table type. If you really want just phenomenal single row, operations, you should use the row store, and that's an option that's available to you. And we use SIMD-based vector similarity functions as well. That's another thing that makes SingleStore vast. We have dot product and Euclidean distance functions for vector similarity that are used for face matching and other uses as well. And I'll talk more about that. So quick example before I get into the details of vector matching. Just a quick example of sort of the level of performance we can get out of SingleStore. So the query on the right is TPCH query 1, and this is a data warehouse style query that's a single table query that's processed against just a line item table from the TPCH benchmark, which is an industry standard data warehousing benchmark. And notice that this query, look at the select list, like it references there are a total of 18 different field references in this query. And if you look at operators like the addition, subtraction, multiplication, there's 12 infix operators. So we process this query against 60 million rows on a one core system in SingleStore Cloud. This is a SingleStore managed service S00, which is the smallest instance we allow you to use. And so just a single core can run that query in 3/4 of a second. So think about that. We process 60 million rows on one core in 3/4 of a second to do all that grouping and aggregation and filtering and all those arithmetic expressions. So how is that even possible? That honestly, that's sort of like science fiction. So, well, it's because we compile queries to machine code and we use excellent vectorization and operations on encoded data. So if you look at the cycles per operator or plus fields, like you count the total arithmetic operations and fields in that query. And we have to touch every single row to do this query and multiply that by the number of rows. The total cycles per operator or field is only 1.41. So that's machine cycles. Like you could do a single instruction typically in a machine cycle. So for each, we only spend 1.4 instructions per field or per arithmetic operator total to do that. So how are we able to do that? We use operations on encoded data and SIMD. So if you look at the profile plan for that query, you'll see proof that we're using operations on encoded data, including for filters and group by. So I just want to talk about this to put in context the operations to do vector matching. So you can use the vector matching combined with other SQL operations, and I'll say more about that later. And the SQL is super fast that surrounds it, and the vector matching is also really fast. Now, focusing in more on vector operations. So SingleStore vector functions are available to perform lots of different things, including things like sorting a vector, summing the elements of a vector, finding the kth element, and so forth. The ones that are most important for the demo I'm going to do today are the vector similarity functions, specifically dot product. And we also have an available function, Euclidean distance. I'm not going to demonstrate today, but that also can allow you to compare two vectors to see how close together they are. The benefits of using these functions includes that they're really fast because we implement them with Intel AVX2 SIMD instructions. And this enables vector-oriented applications like face matching. You can use them for other things like vector, similarity matching can be used for things like product photo matching or text matching. You're basing a vector based on a vector model for text. We have one of our customers is using these functions to do a value at risk calculation in the financial sector, and big trading organizations use the value at risk calculation to make sure they're not like overbuying, a single company. They don't want to accidentally buy, like 50% of one company if they have 7 different trading desks that all decided to take a big position at the same time. So that's just one example of the many things people can do. So if you look at the picture on the right, dot product is basically you pairwise multiply each element of 2 different vectors, and then you sum the results. So the dot product of these 2 vectors turns out to be 1, because we got 0 times 0 is 0, 1 times 1 is 1, 0 times 0.5 is 0, 1 times 0 is 0, and then we add them up and we get 1. Where vectorization or comes in with use of SIMD is that we can process with SIMD multiple operations at a time. So we can do like all these multiplies together in a single instruction, multiple data instruction, and then add up the results. So we can do like 8 concurrent floating point multiplies at a time to speed this up by around more than a factor of 8 compared to doing it with regular instructions. So by building on SIMD, we're able to do really fast AI matching with dot product and Euclidean distance. So now the whole idea of face matching is based on the idea of, face matching with vector similarity is based on a more general concept known as scoring using vector embeddings. So, over the last 20 years or so, a lot of research has gone into creating vector embeddings from high dimensional spaces to lower dimensional spaces in the AI community. And these vector embeddings are typically produced by a deep neural network, like a hidden layer in the deep neural network. So for example, you could have a high dimensional space, like an image could be normalized to be a 256 by 256 matrix of pixels. So the dimensionality of that is really high. 256 times 256 is a big number. But we'd like to reduce the dimension of this, but maintain a lot of the information from the original object in the higher dimension. So using deep neural networks that are trained to do face recognition, we can input into the deep neural network this image, this matrix, and then the output will be a vector. In this case, we're going to do a 128 element vector that is much lower dimension than this 256 by 256. So applications of this are things like face matching, product photo matching, document similarity, and many others. So I'm sure there are many people on the call that know more about AI than I do. You may have in your mind applications you've built already that may not be using a database, but may be using vector similarity based on vector embeddings. Think about how you might be able to use those vectors as data in a database and then use the database system to do high performance matching and do filtering and so forth, mixed with the vector similarity matching to do more in your application, so that you don't have to worry so much about the data management portion of it or the parallelization of the matching. You can rely on SingleStore to do that. So this use of dot product to do vector similarity matching is based on what's known as a cosine similarity metric. And so if you have two vectors in an n-dimensional space, and if they're pointing at sort of like right angles to each other, the cosine of the angle between them is going to be small, like 0. But if they're pointing in almost the same direction, the cosine of the angle between them will be close to 1. So if you do a cosine similarity between two vectors, then again, if the number is high, like 1, that means the vectors are a lot alike, and that's a way to get a similarity match. And you can use dot product to do that in SingleStore. So if you look at, there's an increasing interest in this term cosine similarity. Going back for the last 10 years, you can see that there's like a tremendous increase in the number of times cosine similarity is mentioned out on the internet and in internet searches based on Google Trends data. So now let's do some real face matching in SQL. So suppose we want to get the top 5 closest matches to a query image. I've done this, created a simple demo for this where, we've got a table called people. It's got 3 columns, an ID number, which is a unique ID for each row. and then a file name that contains the file that contains the photo of the person, and then a vector, which is the vector embedding that is sort of represents the meaning of the face in that picture. And those vectors were produced using FaceNet. FaceNet is an open source pre-trained neural network package for face recognition. And you can present a new face to the pre-trained FaceNet network, and it will give you a vector embedding for the face. The cool thing about that is that it's pre-trained on a very large collection of faces, like millions of faces. And so you don't have to train the neural network. You don't really even have to understand the AI behind it. You can just use it in an application to take a normalized picture of a face and produce a vector embedding. And then you can do cosine similarity to measure the closeness of faces. And so we have a blog that Siddharth and I wrote that talks about how to use FaceNet to get vector embeddings for new faces that you might have in your application environment. So this is a blob or binary large object that represents the vector. And we shard on the ID number. So this query, it's a two-step process here. We got one query that finds the vector for Emma Thompson by looking her up in the people table. And then we do this query does a dot product to do a cosine similarity ranked search. So this basically says, find the top 5 closest matching rows to the picture Emma Thompson 1. And I have a little filter here to filter on score greater than 0.1 to make it run a little bit faster. This is optional. I strictly put in the score to make it run faster. And you can order by score, descending, and limit 5. That gives the top 5. So let me actually run this demo. I'm going to go here to, this is the SingleStore managed service, and I'm running this on a SingleStore cloud cluster that has 16 cores. So this isn't really a very big system. So I'm using this database called FaceMatch. I just wanted to show you how many rows I've got in the people table. So there's 16 million rows. And so this is a pretty significant amount of data here, 16 million. And then here's some example file names from the system. So you can see it's based on celebrity data. Bruce Gebhardt, Walter Bondale, Jack Nicholson. These are just sort of randomly selected celebrities from that table. I happen to know that Emma Thompson is in there with there's a few pictures of Emma Thompson. So if I run that, now I have a session variable V that now contains Emma Thompson's vector. And so now let's find the 5 closest matches to Emma Thompson. Let me run that. You see how quick that came back? It was just, almost instantaneous. And so Emma Thompson, the closest match is obviously going to be Emma Thompson 1, because that's the same picture that this vector V represents. So it's essentially 1. This is a double precision floating point number output, but internally it's single precision. So you can ignore the low order digits, but it's 1. So it's a perfect match. And then the closest match with a score of 0.61 is Emma Thompson 2. It's a different picture of Emma Thompson. And see, the 4th closest match is Emma Thompson 3. There was a kind of a false positive here that, Maria Soledad Alvear Valenzuela is a pretty close match, and so is Benazir Bhutto. But the closest match you'll see is Emma Thompson 2. So some interesting things we can do here are we can look at this vector. So select see how this looks. We can unpack that vector into a JSON array. And so you see this particular JSON value. This is a JSON array of floating point numbers. So it's kind of hard. I know it's kind of small there, but this is a 128 element array, and that array of floating point numbers kind of represents the meaning of Emma Thompson's facial structure. And by using that, we can do similarity match against similar faces. So let's go back and continue here. So, all right. So yes, many of you probably know that at the beginning you recognize that was Emma Thompson. So Emma Thompson 1 is the query image. That's the one on the left. And the closest match is Emma Thompson 2. It's pretty cool, right? Because these pictures were not taken on the same day. She's got different clothes, different makeup, or even her hair color is different. Yet it's still recognized that this is the closest match. So this just illustrates the power of modern AI-based facial recognition done using vector similarity and vector embeddings. So some of the benefits of using image matching from SQL are that you can mix the vector similarity operations like dot product and Euclidean distance with all relational operations in SQL, including select, project, join, aggregate, window functions, you name it. So, suppose that you didn't have SingleStore with the ability to do vector similarity matching in the database, but you wanted to do vector similarity matching potentially combined with some other filters or other criteria. How would you do it? You'd have to do it in the application. So you'd have to basically load all that data into your application, into main memory, and then process it in your application. Well, then you're going to start thinking about, hey, can I parallelize that? Maybe I'll do a multi-threaded scan in my application software. And now pretty soon you're writing a parallel database system in your application. You do not want to be in the business of writing a parallel database system. You let the professionals do it. Let us do it for you. You can focus your energy on sort of for example, the data, the semantics of the data, what you want to get out of the data. Using application logic, from your AI portion of your application to get vector embeddings, put that in the database and let the database system parallelize that and do the heavy database lifting. We do some clever stuff, like we reorder filters to put the most selective and cheapest filters first. I mean, this is not trivial. This is something that you might do in your application, but it's just hard work. Let us do it for you. That's the point. So now you might ask, how do I get these vectors into the system? So you and the AI team in your application development world you may already have vector embeddings that you're working with at the application tier to do things like face matching or product photo matching or text sentence matching or word matching. There are many different applications for this, but once you've got them, in order to use the database to do similarity search for your vectors, you first got to get the vectors into the database. The easiest way to do it is to use a built-in function we have called JSON array pack. So this takes a JSON array, then it turns it into a packed binary vector. So look over here on the right. This expression, JSON array pack of 0, 1, 0.5, and 0 as a JSON array, that will create a packed blob representing the vector that has 32 bits per number in this array, and the numbers will be in floating point notation. If I output that in hexadecimal format, you get this. And then S2, just to show you we can go back and forth, if you set S2 to this hex string and then call unhex on it, you get another vector also in the same packed form, and it's going to be the exact same as the contents of V1. And now if I select dot product of V1, V2, I get 1.25, and you can do the math in your head. It's 0 times 0 is 0, 1 times 1 is 1, 0.5 times 0.5 is is 0.25, and then 0 times 0 is 0. So I get 1 plus 0.25 as my dot product. I get 1.25. So this is just a sanity check that the data is going in and out of the vectors as we expect, and we're getting the correct dot product. So you can use JSON array pack and then insert the result into your table. That's the simplest way. You can also insert binary data directly from your app, or if you have data in a hex ASCII string, you can unhex it and put that into the database. So you can just use database insert or bulk load operations to put the data in. And for bulk loading, we have both load data and pipelines, the two different features that you can look up in our documentation. Okay. So now using FaceNet to create vectors in SingleStore DB is something beyond the scope of what I was able to cover today. But Siddharth has built out a whole process for taking images, running them through FaceNet, and then transforming that into a format that you can then load into SingleStore. So he wrote a section in our blog, which you can look at later, that talks about how to take a sort of an open source collection of celebrity images and that are stored in a folder, and then download those, then run FaceNet over it to extract the vector embeddings into another text format. Then you can then load that into SingleStore. So this procedure used Ubuntu Linux, TensorFlow, Python, SciPy, FaceNet, and Image.io. And you can add your own face images to this procedure. You can take out the celebrity images and put your own face images through the same process to do vector matching of face images if you like. And there are many different sort of open source or proprietary AI packages out there that can produce vector embeddings for pictures or other kinds of information. For example, there's another one called VGG Face that is somewhat similar to FaceNet that's also available. And there are other pre-trained networks for object matching. FaceNet happens to be for face matching specifically, so it can't look at an arbitrary object and get a decent vector for it because it's not trained for that. But there are plenty of other software packages out there that can take pictures or other data items and produce vectors that you could insert in SingleStore. So also we do support more than just a 32-bit floating point type for our vectors. The default for our vectors is that we're floating point 32-bit, but we also support 64-bit float, and integer 8, 16, 32, and 64 for dot product. Some customers asked us they said they, for example, wanted to do, I think what they called it was one-hot vectors, where their vectors are all zeros or ones, and they wanted them to be very compact and take less RAM and run faster with SIMD. So you can use i8 for that kind of vector. It just uses an 8-bit integer for each integer. And you can use dot product or Euclidean distance on that, and it can be faster because it can do, in a single AVX2 instruction, it can do 32 one-hot type integer operations. So it'll run faster and take less memory to store the vectors. So just we have every one of our built-in vector functions has versions for all of these, and you have to put the data type as a suffix of the function name in order to use the different data type versions. But for example, we have a JSON array pack underscore I8 routine, and so that's available, and this is all fully documented. So I wanted to talk a little about some customer applications using ones based on object matching in SQL. So a customer of ours is named Nyrus.io, and they used our product to do object recognition to do product catalog search with applications for both industrial catalog search and retail applications. And you can go to their website and see this image on the right. And they also have a YouTube video, and you can see watch that video. I'm not going to play it for you right now, but at 54 seconds in, it shows them, you can just take the smartphone and point, while you're running their app, and point it at an object like a roller bearing like you see on the left, and it will search the product catalog for stuff that looks like that and give you the closest matches. So you can imagine the applications, like if you had a big industrial shop with thousands of spare parts in its spare parts room, you could put that into an image matching system and use Nairis.io to search your spare parts without having to know what the name of the part is or the model number, and that could save tremendous amounts of time. So have a look at that YouTube video, check out Nairis.io for an application of SingleStore, and you might like what their product does. It might be interesting for you. So just to recap, SingleStore leverages modern hardware to deliver amazing query speed. We do code generation to Intel x64 machine instructions. We use Intel SIMD. We use scale out and vectorized query execution. So we're a modern database that can do both in-memory and disk-based column store query execution super fast. And we have the extra capability of being able to do AI vector matching with dot product and Euclidean distance super fast. So the benefits of this are fast interactive response time for both OLTP and analytics, and AI in SQL. You can do 10 to 100 times performance improvement compared to legacy database systems on the same hardware. And this enables just a new generation of applications for operational analytics, transactional and analytical workloads as well. We're trusted by name brand customers like Dell, Siemens, and GE, and many more. So I'd urge you to try SingleStore today. If you haven't tried it already, try it on our cloud. That's the easiest way to get started. So that link takes you to our cloud free trial. If you don't have that link, just Google for SingleStore DB Cloud or SingleStore Cloud. It'll take you straight to this. We also have a free edition for on-prem use. So there's a link to try that free. If you want to host it yourself, you can use that. It supports up to 32 cores and 128 gigs of RAM. It has the same feature set as our standard edition. We also have a premium edition with some additional features like disaster recovery and point-in-time restore, resource governor, and so forth. But most of our features for just query processing and programmability are available in the standard edition. And then SingleStore DB is available as a cluster in a box for development on Intel x64 compatible hardware. This is not supported for production use. It's for developers. Like if you have a PC or an Intel-based Mac, you can use this cluster in a box image and very quickly get started using a Docker image to use SingleStore and develop for SingleStore. And then we also support M1 Max for development and evaluation using a cluster in a box image that runs on the M1. Take a look at that blog. There's a full link to that blog. We have a blog about running SingleStore DB on your Mac M1. And we've also got a blog about how to do image matching that Siddharth and I just recently published. And that goes through the demo that I did and sort of talks about similar things that I talked about in the presentation today. And Siddharth also has a nice section in there on how to use FaceNet and how to set up an environment where you can use FaceNet on your own face images that you might have gotten from your own application environment. So with that, I just want to thank all of you for attending today. And, SingleStore is just an amazing product. Once you get your hands on it and see how fast and interactive it is, you may just be stunned and may think of new things that you want to do with data and vectors that you never thought you could do before. So please give it a try. And now we're open for questions. So let us know if you have any questions.
Awesome. Thank you, Eric. Great presentation. As you mentioned, we're now going to begin the Q&A session. So just a reminder for the audience, the Q&A functionality is on the right-hand side of your console. So feel free to get in there. I will moderate that. First question for Eric here is, you have a dot product function, but what I really want is cosine similarity. How can I get that?
Yeah, so we have a dot product function, but if you normalize all your vectors before you insert them to length 1, just using standard vector math from your geometry textbook, normalize everything to length 1, and then the dot product is equal to the cosine of the angle between two vectors. So that's the best way to do it.
Awesome. Here's one. Is it easy to migrate data from other database systems to SingleStore DB?
Yeah, it's really easy to migrate data from other systems to SingleStore DB. You can do it in a number of different ways. You can export the data into CSV files and then just use the create table statements they used from the original database, maybe with a few tweaks to create the same tables on SingleStore, and then use SingleStore load data or SingleStore pipelines to load that data in SingleStore. If you're coming from MySQL, it's pretty easy. The same create table statements that you run on MySQL can usually be run on SingleStore. You may have to get the best performance, you may want to add a shard key and a sort key if you're loading into column store. So you have to do some thinking about that before you load the data with. And then we have a partner. So we have this. We have a feature called Replicate. So that's a partner technology that's available to all our paying customers. They can use SingleStore Replicate to load data, like to do snapshot load from a source database, be it like Oracle, SQL Server, Postgres, MySQL. So there are a number of different ways to get the data in, but it's pretty easy. The main thing you need to learn is how to use our create table notation and put the appropriate shard key and sort key on your column store tables. And there are explanations of that in our documentation.
Awesome, thank you. Here's another one. Here's one from Otto Wagner. Does TPC have a vector matching benchmark?
That's a good question. Not that I know of. I don't know of any vector matching benchmarks.
All good. Here is one. I have large 0 to 1 vectors, and I don't want them to take up too much RAM. Do I have to use the full 32-bit floating point values for every number in my vector?
No, you don't. You recall that I talked about those. You can use underscore I8, and you can pack the vector so you got like one number per byte instead of one for every 32 bits. So you can use less memory that way. Just use the underscore I8 or whatever precision is appropriate for you. But for 0, 1 vectors, underscore I8 is the best.
Good stuff. Here's another one. Can you elaborate more on the differences between SingleStore DB and other DBs?
Sure. So SingleStore DB, the most databases that people are familiar with are single node databases that have a B tree style access method and store their data on disk. So like Postgres, MySQL, Oracle, SQL Server, IBM DB2, and there are many other databases out there, but it's most common that they use a B tree access method and store their data on disk. So SingleStore has a columnar access method that's seekable. So that's pretty unique. So most of the column-oriented databases out there, all the other ones that I know of, are oriented towards data warehousing or just pure analytics. They're not oriented towards transactional workloads. So SingleStore can do transactions and analytics on ColumnStore, which we've generalized to. We also call ColumnStore universal storage because it can handle a universal set of workloads. So we're faster than those. For OLTP, we're faster than the legacy OLTP style databases that use a B-tree access method. Yeah, if you use our in-memory row store technology, and then if you want to store more data than will fit in RAM, you can use our ColumnStore and still get great performance, kind of on par with the B-tree access methods. And then we can also do pure analytical queries as well, or better than the sort of the other database systems that are based on a ColumnStore access method that are really just for data warehousing.
Good stuff. Here's another question. Are the images stored inside SingleStore database, or is it stored outside and there's a reference to it like an external table?
That's a really good question. So in the application we showed today, we just use a reference to the images. The images are not stored in the database. The vector embeddings of the images are stored in the database. So we had to have application software, and that Siddharth will talks about in our blog. We have an app that we fed the images into the app, and we read out the vector representing the image, and then we inserted the vector into the database, and then associated with each of those vectors is a file name of the original image that that vector is for. And so once you have got the vector, you get the file name associated with it, and then your app could open up that file and present the image. If you wanted to, you could store images in blobs, but you shouldn't do the vector. You wouldn't do the image matching using the images themselves. You do the image matching on the binary vectors that are the vector embeddings for the images.
All right, good stuff. Here's another one from Otto. Since vectors are analogous to spatial coordinates, have you considered using spatial queries and data structures, or does the vectorization and simplicity of dot product yield performance benefits that would outweigh some of the overhead of spatial queries?
No, theoretically you could. We do have a spatial data type, but it's a two-dimensional type. It also aware of the curvature of the Earth, so it's a two-dimensional Earth surface area type spatial data type. And so these vectors that people use for vector embeddings of higher dimensional objects like pictures of faces, they have many more dimensions. Like it's typical to use, say, 128 dimensional vector. So our spatial feature is not aware of higher dimensions, higher than 2 dimensions. So it really would not make sense to use it.
Great. Here's a question from Sandeep. If we created columnar tables in Oracle Exadata, will it be as efficient as SingleStore?
I personally don't have head-to-head data of comparing columnar and Oracle Exadata against SingleStore, but I'm very knowledgeable about vectorized query execution. And I know, we have some patented technology for doing this operations on encoded data that I talked about, where we're actually operating on 64 rows at a time worth of data in a single SIMD instruction. And some other products out there do use SIMD to a limited extent, but I think we're probably the best at using SIMD for query execution. I'm not sure if the Oracle columnar technology has those kind of capabilities. I would imagine we're faster, and I know, I'm not going to name names, but I know of one large telecommunications company that used to use Oracle Exadata, and they switched to use SingleStore when they switched from 4G to 5G wireless, they just had so much more data that they were going to have to buy like 20 racks of Oracle Exadata, and the cost was kind of astronomical. So they're a big customer of ours, and they moved to us because we provided high performance at a better price point compared to Exadata. So that's the best I can answer that. I can't tell you for sure if we're faster than Oracle, but I'm confident it's very likely that we are. I haven't done that test head to head.
Sounds good. I think we might have time for one question, maybe two, one more. So here's one. You use SIMD to speed up your vector functions. Is that available on your cloud service?
Yes, the SIMD is available on our cloud service. So that SIMD, the Intel AVX2 instruction set, is available on pretty much all Intel chips built in the last 6 or 7 years. And so virtually every Intel-based machine and every public cloud has that, and we use it on our cloud service. It's the neat thing about it is that it's built into the standard chips. You don't need a special cloud instance with like a GPU or anything to benefit from this. We've looked at GPUs from time to time, but we haven't felt that time was right to use GPU hardware because it kind of narrows the audience. And we'd rather invest in using something that's widely available, namely the SIMD.
Awesome. Thank you, Eric. I think that is it for the questions. So I will hand it back to Jason to wrap things up.
Well, wonderful. Thank you, Matt and Eric and Siddharth for joining us. And thanks, everybody. This is pretty fascinating stuff. It's kind of crazy. It still blows my mind just like where we are with AI and all this kind of stuff. And I mean, clearly it's a very hot topic right now. So it's really kind of fascinating to talk about it. So thanks, guys, for joining us and showing us kind of all the stuff we can do with it. So I appreciate that. And just wanted to remind you, right after we hop off today, there's going to be a really, really short survey. It's like 3, maybe 5 questions at the most. And it's really just to kind of checking in. How did we do, right? Did you like this? Was it interesting? Did you learn something? So we'd really, really appreciate your help with that. We're all about community here at DZone. Like I said, we really value your feedback. We want to know how we can make these events better for you, how we can make them more relevant for you. So please don't forget to do that. And then again, you can also check out our website, dzone.com/events, for all of our other events coming up this year. We've got virtual roundtables and fireside chats and tons of webinars. And who knows, you might even see us in person at an event this year. You never know. So be sure to check out everything there. Thanks again, Eric, Matt, and Siddharth, and everyone else for joining us. Everyone have a great rest of your week, and we will see you next time.
Thank you. Thank you.